The first talk is by Joyee Ghosh from IIT Delhi, who will be talking about entangled photons and hot atoms.
Hello, everyone. A very good morning. So first of all, thanks to the organizers. ICTS is beautiful, and I think I'm privileged. So thank you, Sourav. Thank you, Saikat, and also Bimalendu. So this is my first time in ICTS, and okay. So I thought for this particular presentation, I thought that since it's my first time and since I don't get to meet this community very often, I thought I'll give it as a mixed bag. So kind of things that we are doing in the group, which is our quantum photonics group, and that's how the title of the talk is. So yeah, that's some news depending on so based on the recent activities in our group. And basically our group focuses on generation of photons, single and entangled. So that is really the focus of the group, and we also do a small experiment on hot atoms. So I'll be speaking about those experiments. So yeah, that's I tried to put it in a few blocks, the kind of things that we do in the group. So the quantum photonics group is basically in the Department of Physics in IIT Delhi, and we have several endeavors. We are starting our research activities. We have progressed a bit in some of those activities. So our main focus, actually, if we say the broad research interest is in quantum and nonlinear photonics. Basically, we are interested in quantum technologies with single and entangled photons, basically their generation, their detection, and their application for quantum communication experiments. So actually, these four blocks are pertaining to these entangled photon generation through the process of spontaneous parametric down conversion, which I'll get into in a couple of slides. So this is a nonlinear optical technique by which you can have signal idler photons, which are correlated in nature. Then you can also have them entangled. And based on these photons, you can do actually beautiful physics. So when we started the group, we had this first project, which was twin photons for quantum information application. Here, we just explored a PPLN waveguide, and we generated telecom photons. And we just started our studies, also understanding how things propagate in a waveguide, and so and so. After that, now we have two challenging projects. One is a fiber-based quantum communication project in which we have, again, telecom photons, but those photons are produced in a waveguide, and the entire experiment is fiber-based WDM integrated kind of a thing, and it's on the workbench. So that is around 1550 nanometers in which the photons are generated. So that's telecom, and that's why fiber-based. Another endeavor is to explore free space quantum communication in which the photons are generated at 800 nanometers. Typically, the wavelengths, IR wavelengths in which we can do free space communication pretty well, and also they are relevant for satellite communication. Now we use different degrees of freedom in these two projects. Like here we use the polarization in order to encode the photonic qubits. Here we use hybrid photons. So not only polarization, but there are also other degrees of freedom, such as orbital angular momentum and several other things. So maybe I'll go into the details when I come to those slides. Apart from that, we actually also explore squeeze light. So this is a portion that we are starting now. And so squeeze light detection, squeeze light actually helps in quantum detection. So the very popular example is, its application in sensing gravitational waves. People know about it already, right? So if in the port where you're detecting the dark port, basically, there, in case if you have squeeze light incorporated, then you can actually go down below the short noise level, and that's how you can enhance the sensitivity of your Michelson interferometer. And therefore you can beat the, you can really do well in that interferometer for. So I'm not going into the details, but that's also like one endeavor in which we are working towards. And we are starting our experiments there. Apart from that, so all these processes actually are based on this SPDC process. Apart from that, we also have interest in exploring silicon nano waveguides, which is in which we have another nonlinear optical technique, which is now depending on the third order nonlinearity of any system. So silicon has a high chi3 component. And here again, we produce the signal and idler photons, just like your SPDC photons. But instead of a single pump, here we have two pumps, and that's why it's called four-wave mixing. So utilizing this aspect and spontaneous four-wave mixing, we again try to generate such photon pairs, and which we can map into some kind of an entangled state like this. So we are currently exploring these silicon nanowave guide designs. Some of those designs have been fabricated. We have a collaboration with IIT Chennai, with Professor B.K. Vijay Krishnadas's group. And there we fabricate these nanowave guides, and we've also done our first experiments to see four-wave mixing where the signal and the idler are generated. So this is, by the way, classical four-wave mixing, and that is, we plan to start it now in our lab using these chip designs. So that is in a nutshell. And apart from all of this, something that's little different and not like we use the semi-classical aspect of it, where we don't use photons as such, but we use it. So light is treated classically, whereas matter is quantum. So that's in the semi-classical regime. So we are also interested in coherent light-matter interaction. So this is one part maybe which I'll try to also talk about in today's thing. So here we explore a rubidium vapor cell, and I'll go on to those experiments also. So this is just a glimpse, some snaps from the lab when it was getting started. We got our space in 2017, and we've really cranked up, and now it looks very, so this one looks a little indisciplined and disorganized, but now it has shaped up well, and we have more things crowding up on the optical table, and actually a couple of more optical tables to come up with. So this is my group, acknowledging whom I don't think I can really justify this talk. This is the hard work of PhD students who are really the workhorse, the force behind this entire, all these endeavors. So there are several students, some of them are involved in some of the projects or the other. So that's how, and we also collaborate with Professor Vivek Venkatraman in electrical engineering in IIT Delhi. We share students, and we also have a couple of postdocs. So for today's talk, actually, this is the outline. First, I will give a brief introduction because this was the first talk, although I don't know if I can justify time, but I'll try to give a brief introduction. And then I'll be going to the techniques of producing single entangled photons, which is really the focus of our group. Then we'll talk about some recent studies, particularly the quantum communication experiments that we are starting and we are in process, basically, pertaining to the DST Quest and the DRDO projects. And then some experiments and studies that we started with rubidium, one piece of work which is simple, but it got some recognition, and we are happy about it because rubidium is a very well-known system, and we are probably the nth researchers who are researching with rubidium. It's already very well studied, but the fact that we started with rubidium is because of a 780 nice tunable laser, which we actually procured because we wanted to produce SPDC photons. Starting from 775 to 1550, we had that laser in the lab. And sometimes when the laser was resting, because the SPDC photon experiment was not, let's say, it was not running, then at that time we thought that we can utilize it, and we can also, have a vapor cell just from Thor Labs and start our experiments with rubidium. That's how we chose rubidium and nothing in particular. So, and lastly, if there's time, actually, I'll speak about this experiment because it might be interesting for the community here. So this was an experiment which is very close to my heart, and I did it during my postdoc. So this was in the year 2011, 13, so on. So just before I joined IIT, and in this experiment, actually, we looked at single photons from an SPDC source that went and talked or interacted with a single ion of calcium, which was trapped in a different lab. And these two systems were looked as single quantum systems that can be clubbed together in a quantum network kind of a scenario. So if there's time, we'll embark upon that. Lots of animations, but there's not much time, so I'm playing them fast. So just to introduce a little bit, yeah, people know already that when we want to enhance the computational power, there are two alternative approaches. One is to interconnect several units to make them larger. The other is to make the components, the size of the components as small as possible. So this is really the direction in which researchers are working. And as you can see here, this is a single molecule transistor. This is basically a benzene ring between two gold electrodes. So really, we've, people have progressed, and this is what you can densely pack onto your IC chips of a computer. Now, everybody knows about the Moore's law. So that tells you that in the history of computational hardware, every 2 years, the number of transistors that you can pack densely on an IC chip, that doubles, right? So in that sense, how many atoms do we need to encode 1 bit of information was the question. And we are already in this regime where we are working with few atoms per bit, basically, right? So when we are talking about a few atoms, we've really truncated size where quantum effects start playing an important role, and they allow for new applications, right? So instead of getting scared, why not take advantage of them? And this gave rise to the field of quantum information processing. So in QI, so just to give you a glimpse, people already know about it. So in classical computation, we use bits, which is a dichotomic system. It can exist in state 1 or 0. And therefore, if you have n bits, there are 2 to the power of n states that you play with. In quantum information, you play with qubits. Qubits can exist in 0 and 1 as before, just like your bits. But in addition to that, it can, because of the superposition principle, you can have infinite number of superpositions that are possible. So if you're from the atomic community, you might be comfortable with the Bloch sphere. If you're from the photon community, we usually speak about the Poincare sphere. So no matter what it is, if you imagine this sphere as the qubit, so the center of this sphere is where the qubit originates, and the tip of that vector can point anywhere on the surface that gives you that particular state, which is a particular superposition. So in that sense, if there are n qubits, you can have 2 to the power of n basis states. And in that perspective, actually, so there is a huge number of basis states that's available, and in terms of which you can actually write down any other arbitrary state. Right, so in this perspective, actually QI, quantum information, is extremely powerful because this helps you to exponentially expand the state space that is available for any kind of computation. Now, so qubits are fine, but which are the physical objects by which we can, where we can encode a qubit? So, so there are ample examples. You have photons, you have atoms, you have electron spins. Now, whenever we are talking about a particular quantum system, we have to talk about the property. So particularly for photons, there are different degrees of freedom. We popularly choose polarization. So here, let's say this is horizontal polarization, this is vertical polarization. Any other superposition of that is diagonal, circular, elliptical, whatsoever. So these are the different basis states in terms of which you can, like you can have your qubits. Apart from polarization, another very popular example, which is that research field is also coming up. It's old, but it's now people are applying it more and more in quantum optics and for such experiments in quantum communication. So they utilize the orbital angular momentum property of photons, and so photons that possess orbital angular momentum, normally we are not thinking about that, but orbital angular momentum is the quantum number L. So when L is not equal to 0, it has a singularity in the center. So there is intensity null, as you can see in all these pictures. And these photons are called twisted photons because their wavefront is not a plane, but it is a helix. So as it propagates. So those are interesting things. And contrary to the polarization, which is only bidimensional, here orbital angular momentum does not have a limitation on the L value. So it can be multidimensional, right? So high dimensional states are possible through this particular degree of freedom, which is becoming very popular. So two-level atoms, again, there are two states. So one can again use it as a qubit. Then there are also electron spins, up and down spins can, I think I will skip this particular slide. So this is just a comparison table. People already know about this. One thing I just wanted to show here, that although there are many things, so there is the principle of superposition and the infinite number of qubits that are possible. So in QI, we also do unitary operation. We use quantum logic gates. And something that is not there in classical information processes is the resource of entanglement, which is there in QI. And utilizing that actually, I think it makes it very powerful. Everybody thinks that. So now the techniques of producing single and entangled photons. So this is actually the popular technique, spontaneous parametric down conversion that I just talked about. It's a second order nonlinear optical technique. And here actually you have a nonlinear medium chi2. So you have a single pump beam of frequency omega p that can be used to pump your crystal, and thereby it splits into two photons of lower frequency, signal and idler. And this happens under the conservation of energy, where the frequencies of the signal and idler should sum up and give you the pump frequency. And it also happens under momentum conservation, where the wave vectors of the signal and idler should sum up and give you the wave vector of the pump. Now, there is little problem with this because of dispersion. So, but there are techniques in nonlinear optics by which you can actually get rid or circumvent this wave vector mismatch. And those are called quasi-phase matching, birefringent phase matching, and so and so. It depends on what type of crystal you are using and what type of phase matching pertains to that. Now, one thing I just wanted to show you that we can do one kind of phase matching in which the signal and the idler photons are type 2 phase match, in the sense that if you are using the polarization property, then the signal and the idler can be such that they have orthogonal polarization. For example, one has H, the other has V. And when such photons are produced, such pairs of photons are produced, we can map them onto by doing, sometimes they are directly possible. If they are emitted in a nonlinear manner, you can directly map them onto the singlet state, or you can do something in your experiment to map them ultimately on, like doing some kind of a post-selection measurement by which you can map them onto such kind of a polarization entanglement state. So these are fascinating, and not only that, there could be other kinds of polarization entanglement that are possible. The all four Bell states, they are all possible with these pairs of photons that are time correlated as well as frequency correlated. Okay, so coming to the experiments, so we the group has two, as I just mentioned. So we explore free space communication as well as fiber communication. In free space, the popular band that we use, that everybody uses, is the optical band, which is around this. So this is the wavelength range, and here actually sources, detectors, everything are pretty well developed. Detectors are also available. Some portable detectors are also available, which are with high efficiency, but these days there are also these superconducting nanowire detectors, which are expensive, but they come with a very high efficiency. On the other hand, in the telecom band, people are usually talking about fiber-based applications. Here, there is a problem with the detectors because they are not so efficient. I'm speaking about the APDs, but again, SN SPD detectors are highly efficient, but they are very bulky and they are also very expensive. So there are pros and cons, but people nevertheless work, and there's a lot of already a lot of, I think, development in all these regimes. So the first endeavor, which is the free space experiment, this is under a DRDO project, and this has a very simple goal, in the sense, like, suppose if two parties, they want to do some quantum communication, this is Alice, this is Bob, and they want to, so Alice is sending Bob photons, and suppose these are encoded in polarization, then usually polarization requires a common shared frame of reference. But let's say if Alice is sitting in one satellite and Bob in the other satellite, and if they rotate with respect to each other, then that shared frame is lost, right? So if you're talking about, if you encode your qubits in polarization, that information might get distorted by the time it reaches Bob. So then this will actually create a problem, especially in QKD kind of experiments, where we are very particular to the polarization state. So one way to circumvent this problem is to use rotationally invariant hybrid photons. So photons not only have polarization, as I mentioned, they also have orbital angular momentum. So if we can somehow, so the polarization is the spin angular momentum, let's say SZ, and OM is the LZ. So if we can have photons in such a way that their spin angular momentum is oppositely handed with respect to the orbital angular momentum, so we can combine them this way, then we can, and let's say we can, so this is called as hybrid encoding. So utilizing both their properties, then we can have them projected onto this total angular momentum state, which is equal to 0, because they are oppositely, so if there is a rotation in any one of them, then the other one actually compensates it. And ultimately, if you're trying to send your information through these hybrid qubits, then that information is still intact. So that is really the idea. And for that, again, we use SPDC, and we use an orbital angular momentum manipulator, which is called a Q plate. Q plate has a topological charge of Q is equal to half, and it gives you double of it. So L is equal to 2Q, which is equal to 1. So it gives you an orbital angular momentum of 1 to the photons, basically. So we started our experiments in PPKTP crystal. This is just a simple introductory slides, because whenever we have a crystal in the lab, SPDC crystal, we first want to see it for second harmonic generation. So SAG is actually the converse of SPDC, for people who don't know this. or not familiar with this, so this is second harmonic generation. In general, it is some frequency generation if the photons are non-degenerate, but if they are degenerate, then it is second harmonic generation. We are interested in producing degenerate photons, which are orthogonally polarized. So that is what. So we first look at SAG, which is a classical experiment. We pump the photons with 800 nanometer, and this is a temperature controlled PPKTP crystal, and output photons are produced at 400 nanometers. And this is typically, people in the community, they know that these are things that we explore. So SAG power as a function of temperature is a sinc function ideally. This has some focusing things. So this is anyway a different thing, because this does not exactly look like a sinc, but there are reasons, because there are focusing issues. So I don't have time to explain that, but we can take it up later on in a detailed question. So the SAG power is also as a function of the pump power. It varies quadratically. So all those things, those routine checkups we did. And after that, we moved on to this experiment with the Q plate. So whenever a Q plate is inserted in your pump beam, so it converts the, let's say, a horizontally polarized beam coming here, which was initially going. So here we just insert the Q plate, it converts it into radial polarization. So what I mean to say is, the horizontally polarized beam, because of this Q plate and because of the way, so the Q plate has in an inhomogeneous manner, there is optic axis alignment in this crystal, and therefore whenever the beam passes through this, it is such that it converts horizontal to radial polarization. So if you look at the beam after this Q plate, it looks like this, where the polarization is in all these arrow directions. So this is, for example, vertical, this is horizontal, this is diagonal, and so on, for example. Now your crystal is actually phase match for type 2, which means for the input polarization, you would need some kind of H plus V in your for your phase matching condition. Y plus Z will give you Y for that. So in the output, when we saw the SAG from this, we saw a 4-lobe structure, which is something like this. And this tells you that there are intensity nulls at these points where phase matching was not satisfied, because you had only either horizontal or vertical polarization here, which did not satisfy your type 2 phase matching condition. And therefore you had only the SAG beam with these 4-lobe structure, and the maxima of these lobes are where exactly the beam is diagonally polarized. So we also tried to theoretically explain this, and yeah. Yeah. Yes, Shubhadan.
This experiment you have done in lab scale, which is like a meter, let's say, distance or something.
Yes.
Like that.
Yes.
But finally, as you said, the application will be in the actual
free
space communication.
Yes.
So my question is, how much this angular momentum will be preserved when you want to send it to the actual free space communication, which is several thousands of kilometers?
Yes, very good. Thanks for that question, Shubhadeep. So actually, we also, we don't have time to talk about everything in this particular talk, but in parallel, we are also exploring the effect of atmospheric turbulence and various other losses, or, also losses due to diffraction and all of that, particularly when you're in a free space propagation, right? So by using spatial light modulators, you can actually program turbulence, let's say, and you can pass your beam. So we have done those experiments in the lab as well. So we have a spatial light modulator. We can program it to produce a hologram that will mimic your, atmospheric turbulence kind of a situation. And you can give the distance also for that. So the amount of turbulence depends on what you program in the space SLM, basically. And we have seen that, yes, the orbital angular momentum does disintegrate, or let's say does get distorted, but it is after, let's say, quite a few, quite a lot of distance. So there have been experiments there. One second. So there have been experiments where people have done this propagation inside a hall of, let's say, 200 meters. And when you encode them in these hybrid qubits, that experiment was like successful. So the OM does get distorted a little bit, but I mean, at least, let's say, for a distance of 200 meters or so, it should still be okay. But if you're talking about kilometers, maybe there'll be a problem. So
but your actual thing was like free space communication between two satellites, the picture what you showed.
Yes, so actually for satellite, you have to do a lot of beam steering, and then there are also considerations whether you would do uplink or downlink and several such things, right? So if you have beam steering, and then I think one has to also correct it from point to point. So those are definitely considerations. But at least practically, I can tell you that this experiment, at least the classical form of this experiment, has been done for a distance of 200 meters and it works fine.
Yeah. So what we see actually in the L equal to 2 mode or 3 mode, so that the intensity goes down drastically. So do you think that is practical? That to have those kind of things for a
Yeah, again, it depends on the distance, because yeah, if the intensity goes down.
After the primary mode, then 2 and 3, we see that
Yeah.
it is almost impossible to see.
That is true. That is true. Yeah, I agree. So long distances will be a thing, but we mainly focus at L equal to 1 and we are just starting off. So we have to.
In radial polarization, the polarization direction changes from point to point.
Huh.
So how it is different from the unpolarized light?
So in unpolarized light?
I mean,
Asha, so unpolarized
there
light,
also
yes.
the direction changes in every.
Yeah, unpolarized light, I think the polarization is random, so there is not a problem. And this one also, so in unpolarized light, there is no singularity at the center. So there is so it's like a Gaussian if you see the transverse. So there is intensity maxima at the center. Here, one signature is whenever you have L not equal to 0, there's always a null because of the phase thing and because of the twisted nature of the wavefront. The wavefront is completely different. It's helical and twisted that way.
Okay.
Yeah. The other counterpart of this radial polarization is the azimuthal polarization, in which you have polarization direction but along the periphery. So it's like that instead of this way. So yeah, so this experiment now we have, now we do it in the forward direction. So we want to pump it with a 400 nanometer light so that we emit photons out of it at 800 nanometers. So this is degenerate photons. And these photons are, by the way, collinear propagating. So we split them with the help of a 50-50 beam splitter, which does not, by the way, distinguish which polarization went which way. And in that sense, so it is H and V here, but after the beam splitter, H can go this way, V can go this way, or vice versa, or both can go this way. Now, since we do coincidence detection, because these are single photon detectors, we actually do post-selection measurement, in the sense we only look at those events where one photon went this way and the other photon went this way. So, depending on this coincident event, let's say there is a successful event, we say that once that event happens, you can say that the state of these biphotons have been mapped onto some kind of an entangled state that looks like your Bell singlet state. So we started our experiments with that, and in order to characterize polarization entanglement, actually you have to do in 3 mutually unbiased bases, HV, DA, RL. That is what we choose in the lab, and those experiments are ongoing, but this is the best result that we have till now. We still have to do tomography, by the way, after this, so that experiment is still remaining. Sorry, I flipped a few slides. Okay. So this is the other project where we are doing things based on fibers, fiber and waveguide based, WDM. So all fiber integrated WDM based kind of setup. And the idea behind this experiment is to go towards a regime of multi-user QKD or multi-user quantum communication. So let's say if you have a broadband photon source here and you split them, and so there are, instead of a single Alice and a single Bob, you have several Alices and several Bobs. So there is a one-to-one talking between them, and one has to also actually characterize entanglement across these individual channels. So that's why this is, in that perspective, it is like a multi-user QKD kind of a scenario. This is how the setup looks on the bench. So the first experiments were, so this is a different kind of a crystal and different kind of phase matching. Here, the thing is, just to distinguish it from the previous one, here the photons are degenerate like before, but this is type 0 phase matching. So the polarization of the signal and the idler, they are the same. That means we cannot distinguish them neither in polarization, neither in frequency, because they're degenerate and they have the same polarization. But we can distinguish them like, so they are degenerate at 1550, but these are broadband. So by some way, if we can separate out the two frequency parts, so let's say the bandwidth goes from 1520 to 1560 nanometers or so. Let's say the center is around 1550. So we can split them via CL band splitter, and then have it, so the signal goes in one on the C band and the idler, let's say, goes in the L band. I'm speaking a little loosely, it's not perfectly CL, but that is what we frequency separate them and then try to see, and then further channelize them through arbitrary wave, through arrayed waveguide gratings. By that, we can discretize those channels and then look forward to entanglement in each channel. So these are just the first few experiments here. Now, since I think I overpassed my time, can I stop this somehow? Sourav, I think I've, but I have a few more slides, huh? Can I go on? Okay. So actually in that experiment, so just if you separate out in a single pass, you will not get any entanglement because there's no distinguishability there. So the idea is to project them onto a SINAC interferometer. So pump the crystal from both sides, and one of the fibers is actually twisted. So the photons, when they come out, so they are always, so the phase matching tells you that the photons are always vertically polarized, both the photons. But since one of these fibers is twisted, you have the photons ultimately HH. So HH and VV photons from both directions, they come and they mix through this fiber beam splitter where they are superposed. Then through the WDM, which is a wavelength division multiplexer, they are separated out from the pump. And then after that, the photons, the signal and the idler, they get separated through the CL band splitter that I was talking about. So in one side, you have one frequency component, and the other side, you have the other frequency component. Then these are single photon detectors. And again, with the help of coincidence counter, you try to see this. And when you see a successful event, we have actually projected the state of these photons, because you don't know from which side what came. So, and you don't know if, so H and V both can go this direction, H and V both can go direction. Only thing is they are separated out in frequency, right? So ultimately with this coincident detection, you project them onto this polarization entangled state. And with our, so this entanglement characterization, of course, is still not done because you need polarization analyzers in each of these arms. So, but for the first experiment, we have started looking at coincident counts from this experiment. And this is typically because the phase matching temperature of the crystal was around 42. This is where we have the highest coincidences from the SINAC. I think I can skip this slide, but can I just start with the rubidium experiment, or 1 or 2 minutes? I'm sorry, huh? There were also questions, by the way, so I can take that liberty a little bit. So we also explore rubidium. I thought I'll just mention it here. So maybe I can skip all these introductory. So it has a multi-level structure, and there are hyperfine levels. And there is an importance about hyperfine pumping. So everybody does Doppler-Broaden spectroscopy in rubidium. So people know about this. This is the D2 line of rubidium at 780 nanometers. So we have a tunable diode laser, and I wanted to flash this slide because this is a small piece of work that got accepted in Clio and will be presented on 17th of this month. So we basically wanted, so we used a 5-level rate equation model to basically model the D2 line absorption spectrum of rubidium, and we wanted to show the effect of hyperfine pumping. So when you do a density matrix semi-classical kind of a treatment, of course, there are lots of equations because there are many levels, and it takes a very long time to computationally understand that. Instead, if you use a simple 5-level rate equation model, you can actually show the effect of hyperfine pumping, and this has an advantage over the 2-level, the susceptibility kind of a model. So that is what we showed, and yeah. So with using this tunable laser, you just, one can also change the beam diameter of this probe beam. This just goes through a rubidium vapor cell, the temperature of which can be controlled, and then the probe beam transmission is recorded by this photodiode. So this is the hyperfine, there are hyperfine ground states and hyperfine excited states. Rubidium exists in the 2 stable isotopes, rubidium 85 and rubidium 87. And from the 2 ground states in each of these rubidium isotopes, there are 4, these 4 dips correspond to the transitions here. Actually, there are several electric dipole allowed transitions, but since these are very closely spaced, you don't get to see this because this is at room temperature, or let's say at higher temperature. So all these individual hyperfine transitions get merged, or let's say, blurred by this Doppler broadening. So all these peaks are actually embedded in this one Doppler broadened peak. So, and now when you use very high probe powers, then we see that, so let's say this is the experiment, the red line, the 5-level model is this dashed line, and this is from the 2-level model, which is the dotted line, which does not actually satisfy the experimental results. So this is the schematic, the energy level schematic that we use. So these are the 2 hyperfine ground levels that one can imagine. One of these ground level is coupled via this probe beam, and it can so it can have transitions to the 3 allowed dipole allowed excited the 3 dipole allowed transitions to the 3 excited hyperfine states. And apart from that, yes, apart from that, there is the other hyperfine ground level which participates and is important because of hyperfine pumping. So the limitations of the 2-level model is actually, in this particular thing, hyperfine pumping is very important because it leads to absorption saturation via population depletion. The 2-level model actually neglects it, and we see that the experimental results are not satisfied by the 2-level model, and it only works for very low probe intensity. The merits of using the 5-level rate equation model, it captures, it includes hyperfine pumping and also transit relaxation, which is very important between the 2 ground states. And this captures the dependence of the probe diameter as well as temperature. And it also correctly predicts low saturation intensity as compared to the 2-level model. So maybe I can just quickly show. So these
I
are,
think we should stop here.
maybe I'll stop. Yeah, okay.
So maybe while Ashok sets up, maybe we can take one thing.
Yeah.
See, what is the mechanism for hyperfine pumping?
What is the mechanism for hyperfine pumping?
Yeah.
So, so when you have a strong probe, so when you have a weak probe, it is kind of fine. But when you have a strong probe, actually it can also get spontaneously emitted to this level, and these are at different energy levels, right? So, so the probe actually, it actually offers a lower saturation intensity as compared to the simple, what you would imagine. In a simple 2-level atom, you don't actually incorporate this particular hyperfine pumping. You only consider, you know, the transitions that are possible from this ground state to the hyperfine levels, but it does not. So whenever the probe pump intensity is really high, then it causes hyperfine pumping, and then it doesn't satisfactorily, actually just using the 2-level model will not satisfy it. So it has to incorporate. So, and of course, all those things are incorporated in your total density matrix equations, which is a semi-classical model, but that takes a very long time because there are several things. So just by using these 5 levels, which are kind of sufficient, we had shown that at least for probe intensities, which are around, let's say, 10 times higher. So not this slide, but
okay, I think we should really cut down and let's carry on this discussion outside.
Okay, fine.